Hello everyone. So in the last class we were talking about these criteria for appraising models, and we came up with 5 criteria, right? The level of description, completeness, cost and ease of use, range of applicability and accuracy. We talked about the level of description, and in looking at all these criteria we basically compared two different kinds of approaches in understanding turbulent flows. So I would say modeling turbulent flows. Even though one is not really a modeling approach, it is a simulation approach, and that one is direct numerical simulation. On the other end of the spectrum, we had mixing length model as our comparison with DNS. So DNS versus mixing length model. We looked at two ends of the extreme in order to make our point in terms of how the criteria would be helpful in choosing a model. So, for instance, in terms of the level of description, that was the first criteria we looked at. Direct numerical simulation resolves all turbulence scales. Mixing length model, which is a RANS based turbulence model, so a Reynolds average Navier-Stokes based turbulence model, does not resolve any turbulent length scale. It models all the length scales. So in that sense, that level of description is different, right? So if you, just to refresh your memory, the level of description talks about U being resolved, so U being obtained in DNS for every realization of turbulent flow, for every realization. And then we can get multi-point statistics, turbulent structures, anything you want. In the mixing length model, on the other hand, what you get is at a mean flow level, because you are modeling all the length scales, turbulent length scales. You are not resolving any length scale. So you don't have any information about 2-point correlations, turbulent structures, PDFs of velocity. None of that you have, because you're only getting information at the mean level. So in that sense, this is limited. The mixing length model is limited. But this is one of the first criteria in terms of choosing the right modeling approach. The next one was completeness. Now, if you want completeness in a model, that is obviously something that you want. From that perspective, DNS is complete. Why? Because it solves the Navier-Stokes equations exactly. All it needs is the material properties like density and viscosity. Once you provide that to the equations, you are ready to solve that equations, and you can just solve it. In that sense, that approach is complete. On the other hand, mixing length model is incomplete. Why do I say that? Because there are certain constants, for example, that are specified in there. Those constants are obtained from empirical relations, from experimental data for a particular class of flows. So the question is, does it apply to other kinds of flows? So that's the question you need to ask. From that perspective, the mixing length model is incomplete. So that's about completeness. The next one was cost and ease of use, and that is what we were covering towards the end of last class. So this table here provides how the complexity of a flow changes with dimensionality and with certain specific approximations. Approximations like statistical stationarity, the boundary layer equations, the use of the boundary layer equations. So you will see the first column there, the dimensionality is shown from 0, 1, 2, 3. And then the use of boundary layer equations, so that is only applicable to certain kinds of flows. So here we are talking about whether the boundary layer equations apply. That's what the second column is about. The third column talks about statistical stationarity. So certain kinds of flows, you can apply statistical stationarity. By doing that, you are removing away the effect of time. Right? You don't have to solve the transient equations, because everything statistics wise stays constant in time. In that sense, you can just obtain the statistics. On the other hand, you will have flows that are not statistically stationary. You would think that these are more complex than statistically stationary flows or boundary layer flows. And within those, the complexity increases as you go down, because the dimensionality is increasing. So that's what we are trying to say. The computational difficulty increases with the statistical dimensionality, and it decreases if the flow is statistically stationary and if the boundary layer equations can be applied. Okay, so those are some examples. Now, in approaches like DNS, the cost, the computational cost, is a really fast increase in the is a rapid increase with Reynolds number. It actually is an increasing function of the Reynolds number. Whereas something like the mixing length model, no matter how much you increase the Reynolds number, the cost does not increase as much. Because what the mixing length model is doing is it is anyway modeling all the length scales. No matter what the Reynolds number is, it is anyway modeling all the length scales. So then why do I need to refine the grid? A RANS based approach like a mixing length model would of course require a grid that should be reasonable enough, but then that depends on the numerical method you're using. The turbulence model itself does not resolve anything. It models all the length scales. So then with Reynolds number, it has actually no influence, meaning the cost is not a function of the Reynolds number. The cost is a function of the numerical method, yes, but not in terms of resolving any new flow features, because it is modeling all the flow features anyway. Now, so there is more to this cost associated with a turbulence modeling approach. So in order to perform a turbulence flow calculation, you can divide the task into two parts, right? One is this development and obtainment of the computer program, okay, and that depends on, and to solve the model equations along with the initial conditions and boundary conditions. And the second one is the execution of the boundary computer program to perform the calculation and obtain the results. So two parts, right? You have to have a program that can do it. Either you have to write it on your own or you have to obtain it from somewhere. There are a lot of free softwares available, free codes available that are open source, that you can use for these kinds of problems. OpenFOAM is an example of a open source code that is available to solve turbulent flows. So, but you still need to obtain and try to learn how to use it. Now, on the other hand, you can obviously write a code from scratch. That's one way to do it. The second part of the task is now executing the program. The execution of the computer program, that depends on what computing resources you have. We'll get to it, but it also matters, there is a cost associated with that. The time to learn how to execute the program, the time to validate the code, the time to obtain right results, to assess whether you're getting the right results or not. Can they be verified? Can they be validated? There is a cost associated with all of that. So the cost and difficulty associated with the first step, that obviously depends on what is available, what are the algorithms available, and in that sense, if you want to develop your own program, the cost can be significant because you're going to spend a lot of time writing a program, but that is going to be a one-time cost. Now, as far as the second part is concerned, as in the execution of the program, the cost and difficulty associated with the second part depends on the computer, amount of human time and skill required, because executing a program, let's say even if you haven't written that program, and even executing a program requires a certain amount of skill. Obviously, you need computing resources for that, but you need a certain amount of skill to execute the program. So there is a cost associated with that as well. Now, here is an example of the cost associated with executing a program, and that has to do with the computing resources, of course. So we have shown here the amount of computation measured in flops, which is floating point operation. So every calculation done on the computer is counted as one floating point operation, one flop. And so what is the number of flops that can be performed in a given time? That depends on the speed of the computer, right? How powerful your computer is. And that can be measured in megaflops, gigaflops, teraflops. So gigaflops is about 10 to the 9. So that means it is able to perform 10 to the 9 floating point operations per second. Teraflops would be 10 to the 12. So 10 to the 12 floating point operations per second. So megaflops is pretty much obsolete at this stage. When Pope wrote his book, gigaflops and teraflops were starting to come. So this table shown here for the machines are in a sense outdated because they are showing only machines up to 2000 and the floating point operations per second for all those computers. But what we are trying to show is a trajectory of how computing resources, how computers have gotten faster and faster over the years. As you can see, in the 1960s, machines like CDC 6000 and 7600 were operating at megaflops, 10 to the 6, 10 to the 7. Then came the Cray in the late 1970s, which started to get into close to gigaflops. Then the Intel, then IBM SP2, these started to get into close to teraflops. So now, in today's day and age, we are talking about machines that have crossed exaflops, which is 10 to the 15. Okay, so but it still shows a trajectory of how fast computers have gotten over the years, right? So what we see is a remarkable rate of increase, a factor of 1,000 in 20 years, and 1,000,000 in 40 years. That's a huge difference, right? So obviously there is no basis for extrapolation because towards the late 80s, 90s, and the beginning of 2000, computing really shot up, but that rate has not kept up over the years. So there is no basis for extrapolation, but we think that that trend is going to continue. Now, keep in mind, as much as we list out the flops of each of these computers, the speed achieved is going to be less than the peak by 1 or 2 orders of magnitude. Okay, so and typically only 20 or 50% of the peak speed is obtained because there are a lot of losses. Even within a computer, there are a lot of losses due to heat, and it gets slower because of that. Other applications being used. Maybe these flops are measured based on very specific application. If you're not using the same application, you might not get that peak flop performance. So that's also there. But nevertheless, this table tells you how fast the computing resources, how fast computers have gotten over 20 years and 40 years. And that is important in understanding how to model turbulent flows. You might ask, what has this got to do with turbulent flows? Well, it is important because if you're trying to solve turbulent flows in any application, you need to know whether you can actually do it. You're trying to resolve all length scales. You're trying to do a DNS, a direct numerical simulation. Do you have the computing resources to do it? And maybe trying to obtain the most accurate solution is unfortunately limited by the computing resources you have. So understanding what resources are out there, understanding what is needed to solve a turbulent flow of a certain Reynolds number is very important, as important as trying to understand the turbulence in the physics itself. I hope this is clear. So as something worthwhile, this is how the trajectory has been. This is the peak speed, how it has gone from over the last 80 years or 80, 90 years, in fact, where you can see what the peak performance is of certain computers. So this is obtained from the supercomputing website, from data that was on there, and you can see how the peak speed is increasing. And you see this trend that it is progressing over the years continuously, and the trend seems to be keeping up. So when we said earlier that even though there is no basis for extrapolation, we think that the trend will continue. The trend is in fact continuing. Pope had information only till here, right? And this is obtained from the supercomputing website, where you can see over the last 30 years, over the last 25 years, how the computing has actually shot up, and it is kept on increasing. So now we are here. We are more than exaflops right now, and the 2025. So teraflops is 10 to the 12 and exaflops is 10 to the 15, and then now you are at 10 to the 18 or so. So significant increase in computer speed. This is based on how the how the number one, the fastest computer versus the 500th computer in the list in terms of speed performs, right? So the orange line is the fastest computer in the world, and the green symbols are basically the 500th in that list. And this is again from the top500.org website, where you can actually look at the supercomputer performance. And the blue, so the blue one, this is the green, I'm sorry. So the green one is the sum of all the top 500 computers. And the blue one, I'm sorry, the blue one is the 500, not the green. The blue one is the 500th, and the orange one is the fastest computer. The blue one is the 500th computer. So you can see the trends even between the first and the 500 keep on increasing steadily, right? So that's a good sign. I mean, we need computing resources. We need the computers to be fast enough in order to solve problems that are of practical applications. And you will see some even now we are not able to solve many of the problems accurately. We can model problems. RANS approach is available. LES is also available. But doing direct numerical simulations for every problem out there is still impossible, right? For a lot of different problems. This is again the distribution of computers in the top 500 list arranged by country. So you will see that the US has the maximum number of supercomputers, and that is not surprising, followed by China, Germany, Japan, France, and so on. And India is down in 18 in terms of the number of computers. This is based on data from June 2016. Obviously, this number is about 10 years ago, but it's interesting to look at how computing has developed in the different countries. So just some additional trivia to get you interested here. So the next criteria that we are going to be looking at is range of applicability. We looked at three so far: the level of description, completeness, cost and ease of use, and the next one is the range of applicability. So not all models are applicable to all flows, right? As in, many models based on velocity spectra or 2-point correlations, they are applicable only to homogeneous turbulence. They are not applicable to any practical kind of flows like pipe flows or jets, for example. So another example is that particular mixing length models make assumptions about the flow geometry in the specification of the mixing length. So I briefed upon this earlier. The mixing length model has to specify a mixing length as an additional parameter. That specification of mixing length comes from empirical data, and its applicability is only confined to certain kinds of flows, because that empirical data is based on certain kinds of flows. So does that mean you can apply it to other flows? Well, technically no, but in the sense, the mixing length model has been applied to a wide range of flows over the years. It's not used as much today, but it has been applied to a wide range of flows over the several decades. And it is all based on constants for the mixing length coming from empirical data of a particular kind of flow, so boundary layer flows. That doesn't mean mixing length can only be applied to boundary layer flows. It's been applied to all kinds of flows: pipe flows, jet flows, and even boundary layer flows or aerodynamics. It's been applied to a wide range of flows. But its range of applicability is only restricted to certain boundary layer flows where the constants are obtained from. I hope you understand this. So that's one way to look at the applicability of certain models. Now, computational requirements also place other limitations on the applicability. So for example, in DNS, the computational requirements rise so sharply that DNS cannot be applied to very high Reynolds number flows. So that means DNS can only be applied because of the limitation in computing resources. It can only be applied to low to moderate Reynolds number flows. So that is also a discussion about applicability. So we talk about range of applicability of the mixing length model in terms of the physics, right? But in terms of the computing resources, DNS also has its range of applicability. Even though it is the most accurate, it solves velocity for every realization of turbulent flow, it still has a limited range in that sense, and that is mostly because of computing resources. Now remember, applicability is different from accuracy, right? Applicability means if the model equations are well posed and can be solved irrespective of how accurate they are. That's what applicability is. Accuracy means you're trying to compare it to a correct data, to a true data, which is experimental data generally. So the next and the fifth and the last criterion is accuracy. Accuracy is a desirable attribute. Obviously, we want our model to be very accurate, and particularly when you compare the model predictions, the model calculations with experimental measurements. So for example, I want to discuss this a little bit more, especially this point. So for instance, the boundary conditions in the calculations need not correspond exactly to what is in the measured flow. For example, maybe in your model, you're modeling it as 2D. And that you can assume so in your calculations. But obviously, experimentally, there is no 2D. It's all 3D, right? So also, another example is that boundary condition some properties will necessarily not be known. And so you have to be estimated or taken from experimental data. So that's an example. So there you are making some approximations. And by making such approximations, you are possibly reducing the accuracy because you are not taking the exact data, right? Another example I want to bring about is, let's say you have a jet, okay? And let's say experimentally you have a jet. Now the jet, this is the nozzle. Experimentally, if you want to do measurements of a jet, you probably have a pipe that comes in. This is a pipe that comes in and is connected to the nozzle, and it's probably a relatively long pipe. That is possible depending on what kind of logistics you have, how much space you have, and you will have a long pipe that goes into a nozzle. Now we are talking about a turbulent jet, right? So the flow has to become turbulent as it goes through the pipe and comes out through the nozzle, right? Because we want to have a turbulent jet at the exit of the nozzle, which means the pipe has to be long enough for the fluid to attain turbulence, meaning it will come in through some kind of tank. For instance, I'm talking practically, this is what happens. It'll come in through some kind of tank. It might be laminar here to begin with, or it might be transitioning, and it eventually has to attain fully developed turbulence, right, by the time it enters the nozzle. Now, what happens when you do a computation of this exact problem? If you do a computation of this exact problem, you might not have the computing resources to simulate this entire part, this entire pipe. You might not have the computing resources to do it because the pipe might be really long. Physically, it is just a matter of pumping water or whatever the fluid is through this pipe. Computationally, you are trying to solve for the flow in this entire pipe. That might not be possible. So then your computational domain starts here. Your computational domain starts here. And typically the norm is that you do want to simulate a little bit of the nozzle. Okay? You do want to include the nozzle in your calculation. That is the norm right now. It wasn't the norm probably 20, 30 years earlier. But now data has shown, literature has shown us that we need to have the nozzle included in order to have accurate calculations. So let's say you will have the nozzle in there, but the nozzle is very short. The fluid does not have enough time to transition to turbulence within the nozzle. So then what do? You try to obtain, and I'm talking computationally, you try to obtain a fully developed turbulent velocity profile from your experiments. You attach that to the computations. And then you say, okay, so now the profile here is a fully developed turbulent velocity profile that is coming out through the nozzle. I am giving you one example. Okay, there are multiple ways to do this, but I'm giving you one example. But in this particular example, the data that you get from the experiments will have to be approximated. Because what kind of profile do you get? You cannot use the instantaneous profile, so you use a mean. And then if it is mean, that means it is smooth. Then how do you apply the fluctuations? Then you will have to provide get the fluctuations from the experimental data. So do you just stop with second order, or do you go to third order and fourth order? So there you are making some approximations in the boundary conditions of the nozzle. So when you make approximations in the boundary conditions of the nozzle, right there you're starting with something that is quote unquote wrong. In the sense, it is an approximation, yes, but you're starting with something that is different from the experiments. And then if you expect your calculations to match the experiments, it might not be possible. Right? So that's the kind of approximation that I'm talking about in the boundary conditions. We'll talk more about the accuracy in the next class as we continue this particular criteria. Thank you.